Hey guys, I hope you're having a great night. I'm Hedgeberg. It is a little bit after midnight, but I wanted to go ahead and get one of these videos rushed in because my patrons just got me up above $50 a month, which means that I now need to make 2 videos a month, and I have wanted to make this lecture for a little while, so I figured let's go ahead and get started. Today is going to be Lecture 3 in the Analog Design Lectures, and we're going to be talking about energy storage elements. I'm going to assume coming into this lecture that you've seen all of the material in Lecture 1, even if you haven't seen the lecture itself before, which is namely resistive grids, Ohm's law, and Kirchhoff's current law / Kirchhoff's voltage law. You don't need to know anything from Lecture 2 for this specific lecture, and you won't need anything from Lecture 2 for a while. But in Lecture 2, we talked about op-amps and op-amp-based circuits. Finally, you're going to need some external knowledge for this if you want to fully appreciate this lecture, which is going to be differential equations, specifically first-order ordinary differential equations. That being said, I will do my best to walk everybody through this in as simple of a way as possible and in as intuitive of a way as possible, because I know that differential equations are complicated. But I also know that for some people that's going to be a stopping point. So if you need to ask for help, feel free to come to the Hedgeberg Streams Discord. Not the streams, the lectures Discord, which I will have a link to in the description. So if that's something that you need help with, please come join us. In addition, what you're going to need to know by the end of this lecture, or what you will be expected to know by the end of this lecture, I should say, is the following. You're going to know about inductors, capacitors, energy storage, in circuits specifically, and the time domain. So, without further ado, let's dig in. So, I drew in the background again. Whoops. Let's add a white layer there. Move this guy up, and there we go. So, what are energy storage elements? Well, we just talked about it in the what you will know by the end of the lecture. They're inductors and capacitors. There are also other ways to store energy in a circuit, but usually when we talk about energy storage elements, we think of inductors and capacitors. I do appear to be drawing at the wrong layer. And capacitors. So when we talk about energy storage, we mean that literally. An inductor and a capacitor are elements that will actually store energy in some form or another and can then release it at a later time. They will build up some form of potential energy which can then be released. In a lot of these systems, there is a good mechanical parallel that you can think of, which is the concept of potential energy, usually thought of with a hill and a ball at the top of the hill. The potential energy is the amount of energy that's formed, or is the amount of energy that is latent in the ball that will be released by the ball rolling down the hill. So, for most of this, that might be a good metaphor to think of this with. Some students do learn best by that kind of metaphor, and there are a lot of parallels in electrical systems. So, the easier thing to talk about is actually capacitors, so I probably should have put those on the left, but oh well. How does a capacitor store energy? Well, we're going to talk about the parallel plate capacitor. What that means is two large metal sheets with a space between them referred to as an insulator. So this gap here, which I'll erase because I'm going to want to draw in there actually, there's no current that can move through there. These are, in effect, electrically isolated. Capacitors work by the idea, or by a similar principle, I should say, to Newton's law, which states that for every action there is an equal and opposite reaction. A capacitor that's hooked up to a voltage source like this, and let's go ahead and put the other side to ground, is going to build up a charge along its surface. Because of the fact that positive charges are going to end up here inside of the metal plate because of the voltage source which is driving this plate. So what's actually happening is that the electrons are being drawn out, leaving behind positive ions. This results in a positive charge. This means that there's going to actually be an electric field from this plate going down. This positive electric field is going to invoke the opposite response on the other plate, drawing in negative charges from the ground. These negative charges are going to have an equal charge to the positive charge, in effect, canceling each other out. The result is that all of the electric field that's built up on this capacitor doesn't radiate out. There's no electric field here or here. In reality, there might be a small one, but a long distance away, the only place where you'll ever see an electric field in a capacitor is between the plates. What this means is that by putting charge here and charge here, you've actually stored energy in the form of an electric field. And this electric field, if we were to go ahead and replace this voltage source with a resistor, would be able to drive a current until all of the energy built up here was expunged. So, when we talk about a capacitor, we talk about it having built up some charge, Q, and of that, you have Q over 2 charge here and negative Q over 2 charge here. And you've built up a net 0 charge in reality. There is 0 electric field surrounding the capacitor. But there is still energy stored in this capacitor, in the electric field that's between those two plates. I'm going to go ahead and erase all of the... maybe I should leave that. Yeah, let's leave that. And I'm going to go ahead and shrink it down a little bit instead. Actually, you know what? I should review and see if I am correct about that and the charge is Q in that sense. It may not be. I'm going to go ahead and say that there's a chance that I am completely wrong on that and that you should be careful with me on that. But also, the good news is that that doesn't matter for this part. If I were to be teaching a physics lecture, that would be a much bigger issue. But we're going to be getting away from the physics in just a second here. In the same way that capacitors store energy in the form of an electric field, inductors store energy in the form of a magnetic field. So let's go ahead and look at a side view here, and then we'll shift to a top view. So an inductor is usually a metal core and then around that, we're going to go ahead and surround it by wire. Let me go ahead and get a color here real quick. Have I ever actually changed? Yes, I have changed colors. We're going to surround this with wire like so, in loops. Now, let's go ahead and, knowing that this is the horizontal view of an inductor, let's go ahead and shift to a vertical view. So we'll say that we've got this, and we've got some coiling here going down. And here's your second port. I'm sorry for my bad usage of the GIMP, but I'm still learning here. The way an inductor works is in some ways the opposite of how a capacitor works. An inductor builds up charge when you move a current through the wire that's wrapped around it. This wire channels the current all the way down, and when you have a current that goes around in a loop, the magnetic field is perpendicular to the plane formed by that loop. This is often called the right-hand rule, which I really can't demonstrate well in this kind of lecture, unfortunately. But the idea is that if you form the direction of the current, or if you form the direction of the current and the direction of the electric field, the magnetic field... No, that's incorrect. Apologies. I am losing my mind here a little bit. Man, I have forgotten this, haven't I? It's been a while since I've dealt with Physics 2 concepts. The main thing to remember in terms of how this is defined is that in a loop of current, the magnetic field is perpendicular to that loop. So if you have a current moving through this loop, and I hope that my forgetting does not make anybody think that this is too hard. It's just that this is one of those things where it is easy to forget over time, and even people who do this professionally sometimes need to remind themselves. I'm not going to do that during this lecture, but I will try to make a correction in the next lecture if I've got something wrong here. But if you have a current moving around this inductor in a loop, so it's coming in like so, and then moving down like so, what you've done is you've created a magnetic field. That magnetic field is going to be imposed on this core, and this core is going to create, or is going to get a short-term magnetic polarity. You're basically going to create a magnet. So inside of this core, this metal beam has become a magnet, and that magnet is going to be purely dependent on the current. So you've stored a magnetic field inside of this inside of this core. The core is actually going to try to revert back to its previous state. And in so doing, if you were to release the current that was formed by putting a resistor in, and put a resistor in parallel, it would actually drive the current the opposite way. So all of a sudden, this inductor has stored energy and releases it in the form of current. What that means is that you have inductors which store energy as a magnetic field and release it as a current. And you have capacitors which store energy as an electric field and release it as a voltage. Now, the voltage and current in a capacitor and inductor are related, similar to how Ohm's law relates resistance to current, or resistance to voltage and current. And so we define some terms to make it possible to define it in the same simple way. Namely, we say that the voltage in an inductor is equal to L, the value of the inductor, which we define in units of henries, times di sub L dt. So this means that the voltage is L times the rate of change of the current in the inductor. In the same vein, the current in an inductor, I should use lowercase I here, sorry, is equal to C, which we define in farads, times the derivative of the voltage through the capacitor with regards to time. So that means that the rate of change of the voltage in a capacitor times the capacitance, as we've defined it, is the current. These values are defined as such, so there's not really a good way to derive these. In effect, capacitance and inductance are rates, and they are, as such, derived to make the mathematics of interacting with them a little bit easier. As you can probably guess, though, it's not going to be as easy as working with resistors because of the fact that we have this derivative element. And yeah, it is going to get complicated. This is why I said that we are going to be getting into differential equations. So let's go ahead and work with an example of how energy storage affects circuits. Let's get the layers toolbar back here. We're going to go ahead and make another transparency layer. Let's go ahead and make that one go away. Why did I have this cursor? Oh well. So I'm going to go ahead and give us an example of what we're going to call an RC circuit. Here, an RC circuit is a circuit with a resistor and a capacitor. We're going to go ahead and give this source, or give this circuit a source, which I'm going to give this little step symbol here, and you'll see why in a second. We're going to have a resistor, R, and we're going to have a capacitor, C. Let's go ahead and add our ground. And let's go ahead and define how our voltage source behaves. The voltage source here is defined as having a voltage with respect to time such that for all times less than 0, the voltage is 0. And then at time t equals 0, the voltage will jump to 1. Let's go ahead and make sure that that's mathematically defined, and we'll define this as Vn as a function of t. Vn as a function of t is equal to 0 volts for t less than or equal to 0, and 1 volt for t greater than 0. What I want to derive here is the output voltage, V out, as a function of t. Give me a second here to drink some coffee, not some tea. Let's keep moving. So, if we wanted to derive the voltage, there's a few things that we can do to start making this simpler. I need to know the voltage for all times negative infinity to positive infinity. So we can break this in to 3 brackets. Because of the fact that for t less than or equal to 0, so from negative infinity up to 0, the voltage applied to this circuit is always 0 volts. What that means is that there is no power supplied to this circuit from the beginning of time up until t equals 0. If there's no energy on the circuit, then that means that there's no energy being dissipated anywhere in here. That means there's no current through this resistor, there's no voltage across this capacitor. Therefore, we can make the assumption that V out is 0 volts for t less than 0. But what about t equals 0? And I'm going to make ourselves a little bit more space here. Hopefully you guys can guess why, or start to form an idea of what this is going to be for time greater than 0. Well, solving for t equals 0 actually isn't terribly challenging because of the fact that even at the moment that this impulse is applied, even at the moment that this step, and I should say, by the way, sorry, I almost forgot, the step function is called the Heaviside step function, named after a very, very genius scientist named Heaviside, who I would really recommend looking into. Very, very famously under-recognized, but an absolute genius. So at time t equals 0, there isn't any charge in the capacitor. We've defined it as t less than or equal to 0 here, but even if we had said moved the equals to here, the fact is that even though at the moment this jumps to 1 volt, at t equals 0, there's still no charge on this capacitor. Because at the moment when the voltage has jumped, there is no charge on this capacitor. This capacitor will need time to charge. The voltage across the capacitor is the derivative of the current. Nope, I got that backwards. The current into the capacitor is the derivative of the voltage. The voltage will start to pick up, but right now, the voltage is 0. And so even though the most current that there's ever going to be at the time when this initially turns on is moving in, the capacitor is going to have no charge on it. And no charge across a capacitor means no voltage. So at time t equals 0, the capacitor has 0 volts on it. So the only thing that's not trivial for us to solve here is the case where t is greater than 0. So let's go ahead and say that from here, we know that Vs is no longer 0. Or not Vs, Vn. I am mixing up my source names here. I'm sorry, guys. Vn is our source, and from the time t is greater than 0 on, it is non-zero. That means that there's a current moving through here. So let's go ahead and start to try to solve for V out. So we know that V out here is going to be equal to Vn as a function of t minus the current through this resistor times the resistor itself, so we get the voltage drop. So we're going to have I times R. But wait, the current through this resistor is the same as the current through this capacitor, according to Kirchhoff's current law. That means that we can actually substitute the equation that we have for the current in a capacitor, which, if you'll remember, is IC is equal to C times dVc dt. That means that V out as a function of time is equal to, I'm actually going to go ahead and save us all a little bit of time here and get rid of as the function of time, and we can all assume that that's implied, just so I don't have to keep saying that, is equal to Vn minus C times R times dV dt. And if you notice, V out is the same as VC, so I've gone ahead and substituted dVC for dV out since they're the same value here. Now, we get to differential equations. How do we solve this? There's not an easy way to do this. You can't multiply out by dt like you would if you could separate your variables and then integrate both sides. This is not your simple separable equation. But what we can do is we can put all of our V out based terms on one side. So CR dV out dt. The other side we have V in. And now we set this up in regular form. What that means is that we have all of our output events on one side and all of our input events on the other. What we're going to do now is something that is extremely counterintuitive. So pay close attention here. I'm going to go ahead and add 0 to this side, which, what? Why? What's the value there? What I've done is I have separated this system into its particular and homogeneous components. What on earth does that mean? What it means is that we're actually going to separate this into the system, the force that's being applied on the system, and its response. I made the comparison earlier to Newton's laws of physics, or I should say his laws of motion, as they were originally called. In the same way that slamming into a wall will create a response in the opposite direction of equal magnitude, the system here will respond to the force that is applied. The particular term is also often called the forcing term. I don't actually know if there's another name for the homogeneous term. I've only ever heard homogeneous. But the homogeneous term is the response to the impulse that's applied. So what we're now figuring out is how this input voltage affects the system and how the output voltage pushes back to get the total output voltage. So we're going to split this into its homogeneous and particular parts. Since V in is the forcing term or the particular term, we get V out homogeneous plus R times C times dVOH dt, V out homogeneous again, is equal to 0. So we're just going to go ahead and do part 1 here, which is dealing with the homogeneous case. After that, we'll go ahead and come back and talk about part 2, the particular case, which is VOP plus RC times dVOP over dt is equal to V in. 3, we'll do something called the IVP, or initial value problem. And 4, we'll substitute it all together to derive V out. So let's go ahead and take this to a new page so it's clean and the math is easy to understand. Just remembering all of this. So, part 1 is V out plus RC dV out, I should say homogeneous, VOH over dt is equal to 0. So, how do you solve this? There's not really a good way to do it because you can't integrate 0. And you can't just integrate VO as well because there's nothing to integrate it in terms of. If you try to multiply out dt, you're going to destroy a value over here because of the fact that you're going to be multiplying dt against 0. So all of the standard ways to deal with this don't really work. So what we can do to solve this instead is something really neat. We guess. Namely, we think about the fact that this term plus this term at the end have to be 0, which means that their quote-unquote degree, which we can say, x squared. For example, if x squared were VOH and negative x squared was RC dVOH, these would be equal to 0. But there's no way that works because that's not how calculus works. You can't take the derivative of x squared and get x squared again. But there is something out there you can take the derivative of and get it again. And that is e to the x. So what we're going to do here, if you'll let me go ahead and erase here a little bit to make things a little clearer. Ooh, that's a really big eraser. Is we're going to go ahead and say that VOH is equal to alpha e to the lambda t. Here, alpha and lambda are both variables that we don't know the value of. We will solve for them here right now. But this is our guess. What it will do is if we can go ahead and take this guess and plug it back in to get something that's of the right form, then we know that we just need to solve for the variables after that. So let's go ahead and plug it in. So VOH plus RC dVOH over dt is equal to alpha e to the lambda t plus RC times the derivative, which is alpha lambda e to the lambda t. And all of this is equal to 0. Now, let's go ahead and pull out alpha e to the lambda t. What this will give us is 1 plus lambda RC. Now we have something interesting. Because of the fact that we're doing multiples, one of these three terms has to equal 0. One of these terms can never equal 0, and that's e to the lambda t. It's not doable unless t is positive infinity. If it's negative infinity, you're going to get not a number. You're going to get an undefined value because you're going to be dividing by 0. But unless t is infinity, and we know it's not because this also has to work for time just greater than 0, this value isn't 0. And alpha could be 0, but that would mean that VOH is 0, and that means that the circuit is never outputting anything. And we know it has to because of the fact that the values that we have for our R and C are not open circuits, so there is some current at some point. If alpha is equal to 0, we call that the trivial solution. And it is a solution to this system, assuming that R and C allow for it, but it is not the correct solution that we want in a lot of cases. So that means that this has to be equal to 0. So let's go ahead and subtract 1 from both sides, and we get lambda RC is equal to -1, which means that lambda is equal to -1 over RC. And there we go. We've solved for lambda such that this guess can actually work. So we'll move on saying that the homogeneous term is equal to alpha e to the negative t over RC. Cool. Let's move on to the particular solution. By the same concept, we actually get very lucky on the particular solution. So VOP plus RC d VOP dt is equal to Vin for t greater than 0 specifically. Vin for t greater than 0 is a constant, which we'll say is k. That means that VOP plus RC dVOP over dt is equal to a constant. That means that even though we'd be taking a derivative, the term on the left has to be equal to the term on the right, meaning that they can't have varying degrees, or else we'll never get this term on the right, which means that this must be 0, and for a constant, if you take the derivative, you get 0, which means that this term, we're going to go ahead and say that VOP will be, we'll set VOP for our guess equal to beta, and we get beta plus RC d over dt of beta is equal to k, which means that all of this goes to 0 because you're taking the derivative of a constant, giving you beta equals k. So VOP is equal to k, which here is 1 volt, but we'll leave it symbolic just for now. So wait, the particular solution is that simple? Yeah, basically. You'll see this a lot where the particular solution is a lot easier to understand, and it looks more similar to the input term, especially in ordinary differential equations, but in a lot of other differential equations as well. Let's go ahead and make a new layer here. Let's go ahead and bring our two pieces together. Because of the fact that we split it earlier, VO is equal to VOH plus VOP. Here, that means VOH, we know, is alpha e to the negative t over RC. And VOP, it's k. And this means we're actually almost all the way there. All of our variables are solved for except alpha. And we can solve for alpha really easily. I should put parentheses there so I'm consistent, by solving the individual value problem. We know that at time t equals 0, V out is also equal to 0. This makes things really easy. We know that V out at t equals 0 is equal to 0. That's equal to alpha e to the negative 0 over RC plus k. E to the negative 0 over RC is 1, which means that 0 is equal to alpha plus k, meaning alpha is equal to negative k. So we solve for our final variable, and now we can come over here to step 4, finalize, and simplify. V out is equal to negative k e to the negative t over RC plus k, which is equal to k times 1 minus e to the negative t over RC. Here we know k is 1 volt, so the response here, if we graph it, similar to how we did the input, I'm actually going to go ahead and take a second here to graph the input first so you can see the way that this responds. Go ahead and pull this up over here. So the first thing we're going to do is take our input. Let's grab it. Wait, nope, that's not where the colors are. Colors are here. Let's make this green. So green is our input term, our heaviside step function. I'm going to make the next one blue. This plots like such. Oh, that blue's a little bit harder to see than I was hoping it would be. That should not peek over that. Let me go ahead and change that to be a little bit cleaner. This convergence from 0 towards the value. is called exponential decay. What's happening is that as the capacitor builds up charge, the current into the capacitor is decreasing because the voltage difference from V in to V out has decreased. That means that as time goes on, current drops, so the rate of charge decreases, and you slowly converge to the value that you want. Exponential decay always takes this form of e to the negative, it's either going to take the form 1 minus e to the negative t over RC, or if we were to go ahead and do this with an inductor instead, which we can quickly do, let's go ahead and hop over to the next page. We'll go ahead and make us an inverted Heaviside step function. In the case of an inverted Heaviside step function, if we say V in as a function of t is equal to 1 volt for t less than or equal to 0, and 0 volts for t greater than 0, then we actually know that lost my train of thought there. Let's go ahead and make our circuit first before I try to explain too much here. So our inverse Heaviside step function, we have our resistor here. We have our inductor, which looks like this. R, L. And we're going to do very much the same thing. So we know that V out as a function of t is equal to, if we say that this has been 1 volt this whole time, an inductor charges up to a value over time, and it gains current over time, and so an inductor will start to look like a short. This means that, wait, have I generated a problem which is going to look exactly the same as the previous one? I have. Yes, I have. Whoops. Wait. Yeah, I have. I was not thinking here. I need to actually invert this, and we need to make the step function exactly the same. I am sorry. Please ignore that, guys. Not thinking here. It's getting late. And I've actually been working on applying to a new job, which has had me extremely busy. And it all starts to wear you out after a little while. My deepest apologies. So, if we go ahead and make our LC circuit, or our RL circuit, I'm sorry. L, R. The inductor has no voltage across it initially because of the fact that, like in the previous circuit, there's no charge in this circuit before t equals 0. That means that, as with everything, the voltage across L at time t equals 0 and before, well, no, not at time t equals 0, actually. The voltage across an inductor here in this circuit for time t less than 0, I need to move the equal sign over to make sure that I don't make anything too unclear. So let me go ahead and quickly, oh, why am I using the eraser there? I could use my pen eraser. Again, I hope nobody minds me making a couple little mistakes. It's going to happen. I do not edit these before they go up, partly because of the fact that I don't have the time, and I think it's more genuine. I think it's, for a few people, it might actually be reassuring to see people make mistakes, to be totally honest. So, 0 volts for t less than 0. And then, for t equals 0, something interesting is going to happen here. At the moment that the power switches on to the circuit, all of a sudden, you have a voltage here. An inductor charges in terms of current, which means that it will try to hold its the current that it has at the time. That means that because of the fact that the current through here was 0 all before, the current through here is going to be 0. That means that the current through the resistor is going to be 0, meaning that the voltage on the left and right of the resistor are going to be the same. So it's actually going to be 1 volt at t equals 0. Let me go ahead and expand the curly brackets over here. Oh dear, I have an alarm. I'm sorry, guys. I should be... Oh, wow, I've almost been going for an hour now, haven't I? So, we still have one more thing to solve for, which is for t greater than 0. Should go ahead and clarify over here that this is V out. So how do we solve for this? Same way we did the last one. We know the current through here. Well, actually, this one's a little trickier. We know that V out is equal to VL. And we know that VL is equal to L times DI over DT. Ugh. What am I doing? Get a hold of yourself, Hedgeberg. Okay. And we know that the current here is also equal to V in minus V out over R is equal to I sub L. Sorry guys, quick stretch here. It's been a little while since I solved one of these. We have to make sure that we're accounting for all of the nodes in this equation. So what we're going to start off with is V in minus V out is equal to R times I sub L. Oh, right. I know what I'm doing wrong here. I'm sorry, guys. One more second. I'm being a fool. We need to get this in terms of voltage for it to be easily solvable because of the fact that current and voltage don't convert so easily when you're dealing with derivatives. What we're going to do is we're going to say that V out is equal to L times DIL dt, which is equal to dV in over R, or D over dt of V in minus V out over R, which is equal to, well, the derivative Vn is a constant, and we can split this, and so Vn over R is going to derive to 0. So then we just have V out over R and that's going to simplify to, oh, I forgot the L over here. I am just making a ton of mistakes. This is equal to L over R times dVO dt. So that means that VO minus L over R. I'm making another mistake here, aren't I? Yeah, I am. I forgot the positive sign. There we go. When you do these problems so much, you get used to them, but you still make math errors all the time, is equal to 0. So that means that the forcing term here is 0, so we actually only need to solve the homogeneous portion. But you had to do a little bit of math to get here, and I'm not going to claim it was smart math because I screwed it up a lot. So I'm going to say that was probably some dumb math. Anyway, let's go ahead and move on. So we'll go ahead and start by solving the homogeneous portion, which is the same as the particular portion. So we have V out plus L over R dV out dt is equal to 0. In much the same vein, we can go ahead and assume that the solution for V out is equal to alpha e to the lambda t. Now we know that alpha e to the lambda t plus L over R times alpha times lambda e to the lambda t is equal to 0. Now we can go ahead and pull out our terms the same way that we did. Now we can assume that this is a non-trivial case, meaning that we get 1 plus L over R times lambda is equal to 0. And that means that if 1 is equal to L over R lambda, lambda is equal to R over L. So now we've solved for lambda. We don't have a forcing term, so we can jump straight to step 3, which is our individual value, or our initial value problem. And if we go ahead and come back here, our initial value that we can use for t equals 0 is 1 volt. So we know that V out is equal to V in. We'll just leave it as V in just to make it a little bit more symbolic. V out at t equals 0 is equal to V in, which is equal to alpha e to the Yeah, this is correct. Okay, for a moment I almost thought I was making another mistake, but I'm not on this one actually. Is equal to e to the L over R t. Now we know that t is 0, which means that V in is equal to alpha. So here we have V out for t greater than 0. Making a lot of little mistakes here. Is equal to... Man, sorry, I want to make sure that this equation looks right, and I keep making mistakes. For t greater than 0 is equal to V in for t greater than 0 times e to the L over R times t. What is this going to look like? It's going to have a similar exponential decay property to our last problem, but it's going to look like this instead. Let's go ahead and draw our stuff real nice. So I'm going to go ahead and use... No, we used red? No, we used green for the last one. Let's go ahead and draw our nice green heaviside step function. Now let's go ahead. So I'm going to use red because it wasn't as visible last time, even though it gives us kind of weird Christmas colors. At t equals 0, we know that there's no current, like we said. So at t equals 0, the voltage is going to jump Don't want that to rise above the axis and give people the wrong idea. The voltage here is going to jump. Now, as t goes up, e to the L over RT, that should be negative. Yeah, it should. It should over here. I made a mistake on the sign. This should be negative. I'm sorry, guys. Man, just a bundle of mistakes today. And it should be R over L, not L over R. R over L. R over L. I'm sure some of you guys were screaming at the screen while I made that mistake. Whew. Man, I'm so sorry. Might go in and make some annotations. I'll catch that later. But as t increases, e to the negative R over LT is going to decrease. So, for t greater than 0, we're going to start at 1 volt, and then we're going to decrease in the same way, and we're going to decay down to 0. And if you remember what we talked about with inductors, they charge in current. So over time, an inductor is going to look like a short, and a capacitor is going to look like an open circuit. So if an inductor is charging towards being a short, then it makes sense that after a long time, the inductor's current will be limited by the resistor in this circuit. This means that over time, there will be no voltage gap across the inductor. So it makes sense that over time, the inductor is going to charge so that there's 0 volts across it. So this is a simple couple of examples for how to use L and C components. I think you guys probably noticed I made a fair number of mistakes there. I made a not insignificant number of mistakes there, and I'm sorry for that. I'm not going to lie, it's hard to keep all your variables straight when you're doing differential equations. And for those of you who quite possibly did not know this already, you're going to be looking at your screen wondering what the hell just happened. Yeah, understood. The good news is that next lecture we're going to cover something that makes all of this obsolete. We talked about the time domain, or we didn't talk about the time domain actually, did we? All of this that we're talking about is in the time domain. It's the way that the circuit responds over time. The good news is that after this, we'll switch into the frequency domain. What that means is that we won't analyze these circuits in the way that we just did. We'll be able to go back and use something much closer to Ohm's law. And we'll get into all of that in lecture 4. That being said, this is how these circuits respond in time domain. If you apply a stimulus to one of these circuits, they're going to converge to a behavior over time. And that's what a time domain response is. So when we talk about time domain circuit analysis of energy storage systems, this is what we're talking about. So what we covered today can be summarized as follows. We talked about, let me go ahead and get back to black here. We talked about time domain a little bit there at the end, but you'll understand a little bit better what I mean by domain next lecture. We talked about inductors, L, and capacitors, C. And we also talked about RL/RC circuits and how they build up and release energy over time. So that's going to be all for us for today. So what we're going to talk about for next lecture is going to be the frequency domain. And almost the entire lecture is going to be spent on frequency domain analysis and something really cool sounding called phasors. think there's a Z in there. So we will talk about all of this next lecture. Until then, though, we're good to go for now. So I want to go ahead and thank you guys all for tuning in. I know it was probably a little bit weird and a little bit frustrating for a lot of that. And I also apologize for making so many mistakes. If you have any questions, I'm going to beg you with both of my hands together. I'm going to beg you to come and ask questions in the Discord that we made for these lectures, which I have provided the link for in the description. So if you have questions, there's some really smart people there. Or if you'd like to answer questions, please come hang out there. I get a notification whenever anybody asks a question there. I will try to have your question answered within 15 minutes if I'm awake. So if you have questions, please come and ask them. In addition, if you'd like to know when these videos come out, you can follow me on Twitter. My link's in the description as well. Or, if you really appreciate it, you can subscribe on Patreon, and I would really appreciate that. At the next goal, I'll be able to go ahead and be, that'll be at $100 a month, and I will be recording one of these videos every week. So it'll mean that we'll be getting through more material faster. So I think that's everything, guys. So I'm going to go ahead and wish you best of luck. I think that there was enough weird material covered there that I'm not going to assign any practice problem so much as I am going to ask you to watch the derivations on those differential equations before and make sure that you understood them. And if you did not, I want you to come to the Discord and ask. I like that curly Q I did there. So, I'll go ahead and see you guys in Lecture 4. And until next time, have a good one. If you have any questions, feel free to come and talk to us in the Discord. And I will see you guys next time. See ya.